Kia ora, here's video, I think, number 5 of the Caltech qualifying round for the Integration B 2024. So I'm going to do 2 problems in this video. They're both ones that I think could come up at A level. So they use 2 techniques that we use a lot in the A level curriculum. I'm not going to tell you that until you've had a look at the questions. So pause the video and just see what you think you might do to start with each of those 2 problems. Okay, so hopefully what you spotted is that the 2 techniques we're going to use in here are partial fractions and then integration by parts. The second problem has got, we have to do a little bit of looking at it before we kind of dive in and try to integrate. In the first one, it should be reasonably obvious that what we are going to do is to split this up into the sum of 2 linear terms. Okay, and the reason we're going to do that is when we look at that integral, so we've got 3x plus 4 over x squared plus 4x plus 3. The first thing that I check when I see an integral like this is I look at the denominator, I differentiate it, and I get 2x plus 4. And if I've got that or a multiple of that sitting in the numerator, then I'm good to go. I've got an easy log integral. But here I haven't got that. So where I'm going to start instead is by trying to factorize that x squared plus 4x plus 3. So we can do that easily. We can write this as 3x plus 4 over x plus 1 times x plus 3. And that means that because the order of the numerator is lower, the order of the numerator is 1 and the order of the denominator is 2, we can split this up into 2 partial fractions like this. And if you haven't done this before, go watch my 5 partial fractions videos to get going. Now, we can do this in a couple of different ways, but in both of them, the first step is going to be to say 3x plus 4 has to equal big A times x plus 3 plus big B times x plus 1. Now, I can either do some simple simultaneous equations matching of coefficients here, or I can substitute values in. I'm going to do both methods in this video. So the first thing we can say is that we've got 3x has to equal ax plus bx. So 3 equals a plus b. And matching on the constant, we can say that 4 has to equal 3a plus b. Substituting b is equal to, what did I do? B is equal to 3 minus a. So we get 4 is equal to 3a plus 3 minus a, which gives us 1 is equal to 2a, which means that a is equal to a half. And that gives us straight away that b is equal to 5 over 2. So that's one way to do it. I actually don't usually use the simultaneous equations method, but it's a good method. I think especially when you're starting out, it makes it really, really clear what's going on. So we know that our values are going to end up being a is a half and b is 5 over 2, but I'm just going to do that the usual way that we use, which is to choose x values to substitute in. So, oh, where's my pen gone? Okay. So let x equal -1. That means that we can substitute in that value here. So we get -3 plus 4 is equal to, sorry, I'm just going to change that to a normal equal sign because now we're doing it for one specific value. What have I got? I've got a times -1 plus 3 plus 0 in here. So we get 1 is equal to 2a. That gives me a is equal to a half. To get b, probably the fastest thing to do is to substitute this in and use matching. Or I could substitute in x is equal to -3 and do what we did here. Substitute x is -3 in there. You'll get a 0 coming in here, and then you'll get something else there. Okay, well, what a big mess. But all we needed to do there was to find my values of a and b. So I'm just going to get rid of all of that, and I'll use that space. Ugh. Okay, there we go. Right, so now we're ready to integrate, and it's probably, I reckon, one of the easiest ones that's been in this integration qualifying round. So we've got the integral between, what was it, I think 3 and 0. So writing the whole thing out nicely, we get the integral between 3 and 0 of a half of 1 over x plus 1 plus 5 over 2 times x plus 3 dx. And this is now back to a achieved level 3 NCEA question. We've got a half times the natural log of x plus 1 plus 5 over 2 times the natural log of x plus 3. I'm going to work through this because there's some quite nice practice at log simplification. Again, that's a skill that is at achieved level 3 in the complex numbers and algebra paper, but it's always worth doing it properly. So in here we get a half times the natural log of 4 plus 5 over 2 times the natural log of 6 minus a half ln of 1 plus 5 over 2 ln of 3. So what's cool here is that we can do a bit of work with like terms. This is obviously going to be 0. I can write a half of log 4 as the natural log of 2. And here I can split this up to be 5 over 2 log of 3 plus log of 2 minus 5 over 2 ln of 3. And so then we get some nice disappearing of the log 3 terms, and we get ln of 2 plus 5 over 2 ln of 2, which gives me a final answer of 7 over 2 ln of 2. Right, okay, on to the next question, which is more interesting. So let's just have a bit of a look before we get started. Well, straight up, I'm feeling like this is going to be integration by parts because I've got something that looks like a product, and it's got some bits that might be okay, so maybe we can get there with this bit. Something weird is happening to my pen. Hang on. Right, so this bit here, that looks like it might be okay. I'm not liking that tan squared of x at all, because when I try and integrate that, or even when I'm trying to differentiate it, I've got some bad chain rule stuff going on. So when you see a tan squared in a problem like this, you should be thinking straight away about your Pythagoras trig identities. And we're going to see if that helps me at all, especially if I can get my stupid stylus to work properly. Okay, so sine squared plus cos squared is equal to 1 is my starting point. If I'm working with a tan squared, I'll divide everything through by cosine squared, and that generates me a tan squared of x here. I'll just go further down here and get a bit more space. Okay, so this is where we want to end up. We want to integrate e to the x times tan of x plus tan squared of x minus x dx. I'm just going to check that I've got those signs correct. I think it was a plus plus minus. Yep, it is. Okay, so I'm going to replace the tan squared of x. So we've got this tan squared of x plus 1 is equal to sec squared of x. So that means that tan squared of x is equal to sec squared of x minus 1. So let's write that into my integral and then have another look. E to the x times tan of x plus sec squared of x minus 1 minus x dx. So we could split that up and go through and do a whole lot of integration by parts. But there's a much, much cooler way to do this. And it's just about taking your time when you're looking at a problem like this. Just have a look more closely at this and notice that we've got tan of x here and we've got its derivative sec squared of x here. And then over here, we've got x here and we've got 1 here. So let's just reorder this and see if that helps. And if you watched some of the earlier videos, this should be reminding you of, I think it was question 8, 9 or 10. If we reorder this, we can write this as tan of x minus x plus sec squared of x minus 1 dx. Now looking ahead to when we do integration by parts, you know that we're going to probably end up integrating this and leaving or differentiating this stuff in here. When we differentiate tan of x minus x, we're going to be getting sec squared of x minus 1. And that's going to be coming through as a subtraction. And if you've done lots and lots of integration by parts practice, this should be making sense. If you're just starting out with IBP, this is quite a hard place to start. So go and do tons and tons of practice at easier integration by parts problems. And that will help your brain to start spotting the patterns. I'm going to split this up into two separate integrals now. So we'll have this one here, and then we'll have this one here, e to the x times sec squared of x minus 1 dx. Right, so let's get going on the IBP here. We're going to integrate this, we're going to leave this, and then integrate this and differentiate this. So this first one will give me, integrating e to the x gets e to the x, and then we leave tan x minus x. We evaluate that at 1 and 0, and now we subtract the integral between 1 and 0 of e to the x, and this time we differentiate this. And look, we've got the same lovely pattern happening that we had in question 8, 9 or 10, where the icky bit that we haven't done yet is going to simplify away, right? So let's just see why that's happening. We've got minus all of this, and then we've got plus the same thing. Okay, so they go to 0. And that means that my final answer is a really nice simple e times tan of 1 minus 1 minus e to the 0 times 0 minus 0. So this bit here is 0. So my final answer is e times tan of 1, take away 1. Okay, there you go. A couple more problems left to do. I'm not going to get to them tonight. I'll have a go at them tomorrow. Thanks for watching. And if you're in 13 MCA in 2026 or Skull Calc or the Saturday class, leave me a comment and let me know how you found that second one and whether you could do it without any of the hints.